Okay, yesterday we did this half adder and full adder. I will just once more explain what is this half adder and what is this full adder. Okay, so for making the circuits in half adder and full adder, we are using the sum of products. So what is sum of products means first we have to do the product and then we have to add everything. So that becomes sum of products. Okay. So if I give an example in the Boolean, so these are the products A into B dash into C, and A into B dash into C dash. Okay. So these are the product terms. And first we do the product terms and then we do the summation of that. So that becomes our sum of product. Okay. We can also do it with product of sum, but that is little bit confusing. That's why we are not using the sum product of sum. So if we have only one input, so how can we write this one input? So only A will be the input. So our combinations will be 2 to the power n. So only one is there. So 2 to the power n, it means it is 2. So two type of combinations will be there. One will be 0 and one will be 1. Okay. So how we can write this 0? We can write it as A dash or A bar. And 1 we can write as A. Similarly, if we have two inputs A and B, so the combination will be 2 to the power n. So the number of input is 2. So 2 to the power 2, it will be 4. Okay. So the combinations will be 0, 0, 0, 1, 1, 0, and 1, 1. So how can we write this 0, 0? It will be A naught into B naught or A dash into B dash. The 0, 1 we can write as A dash into B. This 1, 0 we can write as A into B dash. We are using this dash for 0 and simply writing A for this 1. Okay. And if 1, 1 is there, we will write it as A into B. Similarly, if we have three inputs. So inputs are A, B, and C. So we will have total of 2 to the power 3 combinations. So we will have 8 combinations. So the different combinations we can write it as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So all these we can write it like this, like it is 0, 0, 0. So we can write A dash, B dash into C dash. Okay. Or we can write as A naught into B naught into C naught. So for the 001, we can write it as A dash into B dash into C, or we can write A bar into B bar into C. And here for the last, we can write all are 1. So we will write A into B into C. Okay. So for this, we are using this sum of products. So we also call sum of products as min term. So whatever we did earlier, so this min term we represent it with small m, and we will product all the inputs. Okay, so it will be A dash into B dash into C dash, whatever we did. So we will product all the sum, and wherever our output 1 is coming, we will add all those terms. And here is the product of sum. So it is just opposite of this sum of products. So here, instead of A bar, B bar, C bar, we are only writing A plus B plus C, and we will sum all the inputs. So as it is opposite, that's why we are not using this product of sum. Okay, we are using only sum of products. So there are rules for sum of product. We have to uh, and get all the inputs, and then wherever we are getting one, we will combine everything with this OR gate, or we will do the summation. So first we will do the products, which is AND gate, and then we will add everything, which is OR gate. Okay, so this is what we are using in sum of products, and we have to observe only the conditions where we are getting the output as 1, and that is also called as min term. Whereas in product of sum, it becomes opposite. We have to observe for the conditions where the output is 0, and that is called max term. And we have to OR get the inputs or summation of the inputs, and then we have to combine all the cases with AND gate, which means which that is the product. So first we have to do the summation, uh, then we have to do the product. So that's why it's called as product of sum. Sorry, here I have to write. So we are not going to use this product of sum. So here is the implementation of sum of product. So wherever we are getting one, we have to take the inputs for those conditions. Okay. So here we are getting one. So this is first case, this is second case, and this is third case. So for first case, we are getting as 0, 0, 1. So it will become as a dash into b dash into c. So this is the first term we took. The second term, it is, we will see the inputs. So it is 0, 1, 1. Okay. So we will take the conditions for these inputs. It will be a dash into b into c. So we will take the second product, and we will see here we have the third case where we are getting 1. So the combinations are 1, 0, 1. Okay. So the in boolean it will be a into b dash into c. So we are using taking this third product, and what we are doing, we are doing the summation of this. So we will sum this up. Okay. So this is the rule for sum of product. So half adder, as I told you yesterday, it has two inputs and two outputs. One is sum and one is carry. So here we are using this Boolean addition. So if we add 0 plus 0, we are getting a 0. If we add 0 plus 1, we are getting a 1. If we add 1 plus 0, then we are getting a 1. And if we add 1 plus 1, we are getting 1, 0. This is not 10, this is 1, 0. Okay. And if we add 1 plus 1 plus 1, then we are getting 1, 1. So why we are getting 1 plus 1 as 1, 0? Because 1 plus 1 is 2. And if we see this binary, if we convert this binary into decimal, so this 0, 0, what does it mean? It means 0 into 2 to the power 0. So we start writing from 2 to the power 0. Okay. And then we do 2 to the power 1 for converting it to from binary to decimal. So if 0, 0 means 0 into 2 to the power 0 plus 0 into 2 to the power 1. So that we are getting a 0. For 1, the combination is 0, 1. So we will multiply this 1 into 2 to the power 0. So that is 1, and 0 into 2 to the power 1, and we will add both of them. So we are getting 0 plus 1. So that's why we are getting a 1. Same way, if we write 1, 0 combination, it means 0 into 2 to the power 0. So that will come as 0, and 1 into 2 to the power 1. So that will be a 2. So 2 plus 1, 2 plus 0, we are getting a 2. Okay. Same way with combination of 1, 1. So 1 into 2 to the power 0, that is a 1. And 1 into 2 to the power 1, that is a 2. So 2 plus 1, it becomes 3. Okay. That's why for 1, 1, we are taking in binary as 1, 0. It means 2. And same way, if we add one more 1, so if we add one more 1 here, so what it will become, 0 plus 1 will be 1, and 1 will come down as 1. That's why we are getting 1 plus 1 plus 1 as 1, 1. Uh, because 1, 1 is also 3, and if we add 1 plus 1 plus 1, then we are getting a 3. 3 ones if we add, so we will get a 3 in the decimal form. Okay. And here 3 is represented in a binary form. So here are the inputs A and B. So if we add 0 plus 0, so we will get a sum of 0 and a carry of 0. If we add 0 plus 1, so we will get a sum of 1 from here. And as there is no carry, so we are writing as 0. If we add 1 plus 0, then we will get a sum of 1 and a carry 0, because as there is no 0 here. But if we add 1 plus 1, then we can see there is a we are getting a 0 and a this 1, 0. So what is this 1? This is a carry. Okay. So we have written sum as 0, and the carry we are getting as 1. So this is how we are getting this half adder. So this is the theory for half adder. Okay, then.
Mom,
Hmm,
mom, in 1 plus 1 case, how is the sum 0, mom?
hmm? Means we are
in the
representing this lower term, this rightmost term as 0. Okay. And what we are saying, one more thing we are saying that this is a carry. So we are naming this as sum and we are naming this as carry because this is a carry. So that's why like we are just naming that.
okay.
Okay. So this is a sum and carry. Okay. So we will implement this half adder and full adder using this logic gates. We can make this half adder and full adder using multiplexers, using diodes, with transistors. Like if we have to produce electricity, we can use solar panel. Okay. So like to produce electricity, we need this solar panel. Okay. So like that, to make a half adder and full adder, we are implementing this logic gates. Okay. So we are using the sum of products. So first we will AND gate the all the inputs. Okay. First we will see where we the output we are getting as 1. So we will see the inputs where we are getting 1. We will AND gate the inputs and then we will combine all the gates with OR gate. Okay. This is how we are making this half adder, and we will make half adder and full adder in such a way that we have a very small circuit of it. So if we see the sum, so one circuit we will make it out of sum and one circuit we will make out of carry. Okay. So if we see the min terms of the sum, here we are getting a 1 and here we are getting a 1. Okay. So if we see the min terms, we will see the input for this. It is 0, 1. So what it becomes? It becomes A bar into B or A dash into B. And if we see the second term for the sum, it is coming as 1 0, which means it is A into B dash or A into B bar. So we will take the second term, and here we have two ones, so we will uh, do the sum of products. So we have got our products and we will do the sum. Okay. So if we do this sum, we can see that it is an XOR gate. So instead of making this through these many gates, here we will need one AND gate, here we will need another AND gate, and here we will use another OR gate. Okay. So instead of using three gates, what we will do, we will simply use it through one XOR gate. And same way with carry, here we can see only we are getting one in this last term. Okay. So here only one min term is there, and if we combine this we are getting 1 1. So that will be A into B. So that's why we have only taken A into B over here for the carry. So if we want to implement this half adder using logic gates, one for sum we are getting a, logic gate of XOR gate, and for carry we are getting a logic of AND gate. Okay. We have to just get this table. We have to get this table. So whatever you do, we have to get these will be inputs A and B, and the output will be sum and carry, and these are the outputs we should get. Okay. So we are making this through logic gates. So here is our input A and B. So here we have used XOR gate for our sum, and we have used this AND gate for our carry. So here we have taken inputs as A and B, and here also we have taken inputs as A and B. Okay. So this we will implement in this logisim. So here we have used this XOR gate. Okay, here we have used this XOR gate for summation part and AND gate for our carry part. We can even do this with this full circuit. Okay, so here we will need two AND gates and one OR gate and two NOT gates for making A dash into B dash. So this circuit will become very big. That's why we want to make a smaller circuit. So we only use this part. Okay. So we will go through the truth table. If we go through the truth table. For 0 0, the sum is 0 and the carry should be 0. Okay. So if we do 0 0, then the sum is 0 and the carry is also 0. So what if we do 0 1? Then our sum becomes, we add 0 plus 1. So our sum becomes 1 and the carry becomes 0. So we will use this with all the logic gates. We will see sum as 1 and carry as 0. And here is the IC. So if we do 0 1, then sum is 1 and the carry is 0. Same way, if we do 1 0, then also we will add 1 plus 0. Then the sum will be 0 and the carry will, the sum will be 1 and the carry will be 0. If we do 1 0, then the sum should be 1 and the carry should be 0. Okay. But what is for 1 1? The sum will become 0 and the carry will become 1. Okay. So if we do 1 1, the sum should become 0 and the carry should be 1. So this is how we are getting this half adder. Okay, this we can use in this binary addition. When we are constructing a circuit, so how we will do the addition? We will use this circuit for our binary addition part. Okay. Any doubt in half adder? Yes, no, any doubt in half adder? Any specific doubt?
Oh, ma'am.
Okay, thank you. For half adder, what we were doing, we were using half adders to with only two inputs. Okay, so what happens in full adder? We use three inputs and two outputs. So what are three inputs? A, B, and C in. Okay, we are not writing it C because carry also becomes C. So we usually write it with CI, and so we are having three inputs. So the total combinations will be 8 from 0 0 0 0 0 1. Like this, we will have 8 combinations. Okay. So we will get a sum and a carry. So if we add 0 plus 0 plus 0, we will get a sum of 0 and a carry of 0. But we add 0 plus 0 plus 1, then we will only 1 is there. So we will get a sum of 1 and a carry of 0. Here also 1 1 is there. So we will get a sum of 1 and a carry of 0. Okay. But if we add 0 1 1, here we have two ones. Okay, 0 plus 1 plus 1. So here we are having two ones. So as we have seen earlier, for two ones we are getting a 1 0, which means we are getting a 2. Okay. So here our sum becomes 0 and this carry becomes 1, which is like 1 0. So here we have 1 0 0, the next combination, only one is there. That's why if we add all this, we will get a sum of 1 and a carry of 0. Okay. If we add 1 plus 0 plus 1, so two ones are there. That's why we are getting a carry of 1 and a sum of 0. Here 1 1 0 also has two ones, means we will get a carry of 1 and a sum of 0. But for the last input, we are having 1 plus 1 plus 1. So there are three ones. It means 1 0 plus 1. So that becomes 1 1. Okay. That's why we are getting a sum of 1 and a carry of 1. So this is the theory for this full adder. Okay. This is the theory for full adder. So how can we construct this full adder using logic gates? So we have to get all these outputs for sum and we have to get all these outputs for carry. Okay. So we will use the sum of products here also. So here we are getting a 1 in this part for sum. This is the second term. This is our third case and this is our last case for the sum. Okay. So what we did in sum of products, first we will do the products. So we will see what is the input for what we are getting a 1 here. So that is 0, 0, 1. So it will become a dash into b dash into c. So that can also be written as a bar into b bar into c. So this is our first term. So here we have written as our first term. Again, for the second case, we are getting a 1 over here. So it is a dash into b into c dash, or a bar into b into c bar. So we will write the second term. Then here we are getting a 1. So we will see the all the inputs for this. So what is the input? 1, 0, 0. So it becomes a into b bar into c bar. So this is a third term, and here we are getting a 1. So that is becoming like 1 into 1 into 1. So it is a into b into c. Okay, so this is our last term. So if we simplify this, this is not in the syllabus, that's why I'm not telling. If you do the simplification of the sum, it is coming as C in XOR A XOR B. So this is the simplification for this sum, but you don't have to go in that much depth. So if we do the simplification, it becomes A XOR B XOR C. So this is how we are getting this sum part. Okay. And for this carry part, we will see all the min terms. So here we are getting a 1. So we will see the inputs. What is the input for this 1? So we will see as 0, 1, 1. So it can be written as a bar into b into c. This is the second case where we are getting 1. So we will see all the input. It is 1, 0, 1. It means a into b bar into c. Here is the third case. So we are getting a 1 here. So it is input is 1, 1, 0. So if we combine this 1, 1, 0, we will write it as a into b into c bar. Okay. And this last term is there. If we write this, we can write it as a into b into c. So we will write all these things, and if we simplify this, we will get it as a into b into c into c into a. So here is the simplification of how we will simplify the circuit. This is also not in the syllabus. That's why I'm not teaching this. Okay. Just see, if we simplify this for your knowledge, we will get a into b, a into c, and b into c. So this is how we are getting the simplification for this our carry. Any doubt in this? How we are writing the Boolean equations?
No, ma'am.
In your book, one question is there related to this. Here, this is the question: a logic circuit is to be constructed that will produce a logic 1 output whenever 2 or more of its 3 input are at logic 1. Okay. So here we can say there are 3 inputs. It means it will be A, B, C. Okay. So A, B, C will have these combinations, these 8 combinations. Okay. So what it is saying, it will produce a logic 1 whenever 2 or more of the 3 inputs are at logic 0. So here only 1 1 is there, that's why we are getting a 0. Only 1 1 is there, that's why we are getting a 0. But if 2 ones are there, then we will get a 1, 2 or more. Here also we will see that only 1 1 is there, that's why we are getting a 0. And if here 2 ones are there, that's why we will get a 1. Here also 2 ones are there, that's why we are getting a 1. And here in the last case, we have 3 ones. So 2 or more ones are there, then we will get a 1. So here we will write a 1. So, but if we check this with our this table, we can see that this is same 0, 0, 0, 1, 0, 1, 1, 1. So this is actually our carry table. Okay. So we will implement the sum of products. So here actually they have done with simplification. What they have done, they have not used this 0 part. They have only used this 1 part. Okay. So if we do the combinations in sum of products, it will be A dash into B into C. So actually they have not used this uh, 0 part. So simply they have written as BC. Okay. The second part, they have simply written it as AC. They have not used this B bar. And for this third case, they have written A into B. And this last case, they have written A into B into C. So total output, they have written as BC into AC plus AB plus ABC. So that this is the total equation. And if we implement this in the using this logic gates, so this will be the logic gate with minimum number of logic gates. So here ABC, it will be 1. So they have eliminated this part. Okay. If you combine with any of this, it will be same. It will become 1 plus C. So that will become 1. Okay. So they have eliminated this ABC. If we do simplification, this ABC will get removed. Okay. So first they have done this AC. So we have taken this how many gates we will need for this. So we will get we will need one AND gate for this, we will need one AND gate for this, and we will need one AND gate for this. Okay. And here 2 plus are there. It means it is, we are using this OR gate, 3 input OR gate. Okay. So first we will construct this AC. So here we have put our first AND gate. So here 3 inputs are there, A, B and C. Okay. So from first A we have taken one input, and as it is a C, we have taken this input from C. Okay. So output we are getting from here is A into C. So for second AND gate, we have taken input from B, and one input we have taken from A. So it becomes as A into B or B into A. They both are same. Okay. For third AND gate, we have taken input from this B, and we have taken one input from C. So it becomes B into C, or we can also call it, we can make it as C into B. Both are, will be equal. So here we have this OR gate. So we will use this 3 input OR gates. Here it is not 2 inputs, it is 3 inputs. So we will take AC, we will take this AB, and we will take this B into C. And if we OR gate it, it will come as A into C plus B into A into B plus B into C. Okay. Any doubt in this, how we are doing these circuits?
Ma'am, what about ABC?
Hmm?
ABC plus ABC in last term.
This last term, actually if we simplify this now, it will eliminate this ABC. That's why we are not using this. Okay. You don't have to study simplification. So if we take this AB as common, so it will come as 1 plus C. Okay. So 1 plus C is equal to 1. If we do 1 plus B, that is also 1. 1 plus A, that is also equal to 1. That's why for if we do simplify this, it will become like A into B only.
Okay, ma'am.
Okay, that's why we have eliminated this ABC. Like we have to get the circuit with minimum number of logic gates. That's why we have eliminated this ABC. So we knew that sum we are getting as A XOR B XOR C. Okay. If we do this simplification, we will get Cn XOR A XOR B. Okay. So we will not go into simplification. And for carry, we are getting A into B into plus A into Cn plus B into Cn. Okay. So these are the two circuits for our sum and carry. So we will make the circuits using logic gate. So we will use two XOR gates. So if we XOR A into B, so here A XOR B will come, and then we will use this output here in the input, and we will take a C, then it will become A XOR B XOR C. Okay, so this will become our sum. And for carry, as I told you, we will use 3 AND gates and a OR gate. So this will be our carry output. So we will implement this full adder using this logic gates. See, if we use these many inputs, so many gates we will need. We will need one AND gate, one AND gate, one AND gate, and one AND gate. As there are four AND gates, we will need four input OR gates. So total number of circuits we will need as uh, uh, four AND gates and one OR gate. And here also we can see that A dash and B dash is there, and somewhere C dash is there. So we will need this NOT gate also. So we will need like four AND gates, one OR gate, and three NOT gates. So total it will become like eight logic gates. So why to construct this much big circuit? Our device will become very big. Okay, so instead what we do, we only use this XOR gate to make our circuit smaller. So we will see how XOR gate is working. Okay. So these are the outputs we should get for our full ladder. Okay. So a 0, 0, 0, so sum should be 0 and the carry should be 0. And wherever there is a 1, we should get sum as 1 and carry as 0. Where two ones are there, for this case, then we should get a sum of 0 and a carry of 1. And if three ones are there, then we should get sum of 1 and a carry of 1. Okay. So if we get 0, 0, 0, the sum is 0 and the carry is also 0. If we do 0, 0, 1, the sum is 1 and the carry is 0. If we do 0, 1, 0, then only 1, 1 is there. So 0 plus 1 plus 1, so sum will be 1 and the carry will be 0. And if we do 1, 0, 0, so only 1, 1 is there. So the sum should be 1 and the carry should be 0. Okay. But what if we do two ones? So BC 0, 1, 1, two ones is there. So sum is 0 and the carry will be 1. Okay. If we do 1, 1, 0, so two ones are there. So 1 plus 1. So the sum will become 0 and the carry will become 1. And 1, 0, 1. Here also the sum will become 0 and the carry will become 1. Here we have used the IC. Okay. But what if three ones are there? 1 plus 1 plus 1, it will become 1, 1 because we are getting a 3 in binary. So the sum will become 1 and the carry will also become 1. For 1, 1, 1, the sum should be 1 and the carry should also be 1. Okay. Any doubt till here?
No, ma'am.
So one more circuit is there in your book. I told you, we can implement this full ladder using this diodes, transistors, multiplexers, uh, encoders. Okay, we can implement this circuit. But here we are using two methods. One is through logic gates and one is this with two half adders. Okay, what if we only have half adders? So how we will construct a full adder using this? So here we will use one half adder. Here we will use the second half adder. Okay, for first half adder, we will give input as A and B. And for the sum of this first half adder will go to the second half adder. And here we will take a C, input C in this second half adder. Okay. And the carry part of this half adder will go to this OR gate. And the carry part of this second half adder will go to this OR gate and we will get a carry. And this is how for the sum part of this second half adder, we will get a sum. Okay. So what we have to get? We have to just get these outputs. We have to just get these outputs any way you do it. Okay. So we will see how will this circuit work. So here I have used first half adder. Here I have used for second half adder. For 0, 0, 0, sum is 0, carry is also 0. If we do 0, 0, 1, then the sum will be 1 and the carry will be 0. 0 1 0, the sum will be 1 and the carry will be 0. Okay, if two ones are there, then sum will be 0 and the carry will be 1. And if three ones are there, then the sum should be 1 and the carry should also be 1. So this is the circuit we can use using two half adders. Okay, just remember this part. This is how it is working. You have to we can there is also a derivation how we are using this two half adders using this to make a full adder, but you don't have to go in that much detail. Just remember the circuit. Okay. Any doubt in this half adder and full adder?
No, ma'am.
So in this half adder and full adder, how we are doing? We are seeing the outputs. What are the outputs? Whenever there is a one, we will see the inputs for those things. Okay. So same way we will do for this multiplexer and decoder. So what is a multiplexer? Okay, like if you have a phone at your home, this is the phone of your neighbors. You don't like connect your phone cable to your neighbor's phone and to like other phone. And if a person is in different city, you don't like directly connect one phone to the other phone. What you do, we have a pole outside or a terminal outside where we join uh, all the circuits for this phone. Okay, so that the number of circuits it will become less. And if we like connect one phone to other phone, so many circuits will be there, so it will become like very messy. That's why we are using this terminal to connect all the phones from here, and from this terminal we connect to the switch, and that's how we are calling. So that's what here we can see many inputs are there, and but here only single output is there. Okay, so this terminal, it is called a multiplexer in our digital signals, in our digital system. So it has many inputs and a single output. Okay, so in the multiplexer, it is a device that can receive multiple input signal and synthesize a single output. So here in the multiplexer, we have a select line, and here we have inputs. So this is input select line, and these are the inputs, and we have only one output. So if the select line, first we have to see select line. Okay, if the select line is n, so the number of inputs will become 2 to the power n. Okay, and output will always be 1. So if we have only one select line, the number of inputs will become 2 to the power n. So 2 to the power n will be 2. So it will be d0 and d1. If our select line is 2, then our number of input lines will be 2 to the power n, means 2 to the power 2. Then it will become 2 to the power 2 is 4. So here we will get d0, d1, d2, d3. Okay. Why I'm taking the select line, I will tell you. And if our number of inputs are 3, like A, B, C, then the inputs will become as 2 to the power n, so means 2 to the power 3, that means it is a 8. So we will take this d0 to till d7, and in multiplexer only one output will be there, so only one output will be there. So here how we will write this multiplexer, if two inputs are there and one single output is there, so we will write it as 2 is to 4. If four inputs are there and one output is there, so we will write it as 4 is to 1. And if eight inputs are there and one output is there, we will write it as 8 is to 1. Okay, and we don't have to study this 2 into 1 and 4 into 1 in the syllabus. I've just given in this example, but this 8 is to 1 you have to study. Okay, so for 8 is to 1 we have input select line as ABC, or we can say it as S0, S1, S2. Okay, and the different combination inputs will be D0 to D7, and there will be only one output. So if we use the select line, why we are taking here D1 and D0, I will just tell you through the circuit. So here is our input line. Okay, this is S, only one input is there. Here there are 2-bit inputs are there, and here 3-bit inputs are there. Okay, so here it is S, here S0 and S1, here S0, S1, S2, or ABC. Okay, so here if we have only one input, then we are having a select line of D0 and D1. So here actually what we are doing coding. Okay, if I give you example for this, you might have seen the stabilizer. Stabilizer, you know, na? You use it for your TV and fridge.
Yes,
Yes.
ma'am.
Okay, so there are two buttons in there. One is green and one is red. Have you seen that? Two buttons are there.
Yes, ma'am.
So
Yes,
what is
ma'am.
for green and what is for red? Why we are using green and red in the
Output
stabilizer?
and input.
No, when low voltage is there, na, your green signal is working, and
This for
uh,
overload.
when it becomes high voltage, then what, red button it works and TV gets switched off. Okay, so here also like that it is assigned. So here D0 is assigned for our 0 code. Okay, here this S is the code. So 0 is assigned for this D0 and this 1 is assigned for this D1. So if we click here, our code is 0, and if we click on this D0, okay, then both are correct. Means our code is also correct, and this D1 we have put it as 1. This is also correct. Then only it will give us the output. Okay. If we click on this, here the code is 0, but if we click on this 1, then it is not working. See, this is not working. Means our code is wrong, or this whatever we are clicking, that is wrong. Okay, that's why it is not working. But if we make code as 1 and we switch on this D1, then this will work. So this is 2:1 multiplexer. I will show you this 4:1 multiplexer. Okay, so here for 4:1, if we see the combinations, so if two select lines are there, then the combination will be 0 0 0 1 1 0 and 1 1. Okay, so these are 4 combinations. So actually what we do, we assign this 0 0 to this D0, then we assign this 0 1 to this D1, and we assign this 1 0 to this D2, and we assign this 1 1 to this D3. Okay, it is predefined. Like it is already assigned to these things. So if we give a select line or a code of 0 0, and if we switch on this D0, then only we will get a on output. Okay, if we click on any other gates, it is not working. So for 0 1, which one is assigned for 0 1?
D1.
For D,
D1.
D. Okay, so if we click on this D1, then only we are getting a on output. Otherwise, others are not working. For 1 0,
D3.
1 0 will be D2, na? It is starting from D0. Okay, so for 1 0, we will click on this D2, then we will see a output. Any other gates, if we click on, then it is not working. And for last case, we have assigned this D3. Okay, so if we will click on this D3, and if we click on this 1, only then only it will give an output. So it is acting like a comparator. Okay, it is checking what is the code and which switch is on. Only then, if both are matching, only then it is giving an output. So it is working as a comparator. Okay, it is comparing this part. This is true, and this switch is also correct. Whichever switch is on, that is also correct. Only then it is giving an output. Okay. In any other case, it won't give the output. Same way with our 8:1 multiplexer. So this 000, what are the different combinations? It will be 000, 001, 010, 011. These are the combinations. So this first part is assigned to this D0. The second part is assigned to this D1. This third combination is assigned to this D2. And same way, this last 111 is assigned to this D7. Okay. So if we do 000 and if we click on this D0, only then it is working. If we do 001 and we switch on this D1, only then it will work. If we do 010 and we click on this D2, only then it will work. Okay, for any other cases, it is not working. So for last case, we will click on this D7, and what is the combination for last case?
111.
Okay, then we will do the coding as 111. Only then it will give the output. Okay. So understood how it is working? It is working as a comparator. It is checking what is our code, and whatever is assigned, that is switched on. Only then it is giving a 1. Okay. This you understood how it is working as a comparator? How it is working like a comparator? It is checking the code first, and it is checking the switch which is assigned to it, that is on. Only then it is giving an output. If we click on any other switch, it won't give an output for this. Whatever we switch on, it is not giving an output for this. Only if we switch on whichever is assigned to it, only then it is giving an output of 1, means it is correct. So it is comparing this in select line, and it is comparing this input whether it is on or not. Only then it is giving an output. Okay. So we have done this, seen how this is working. So how we will construct the this circuit? Okay, so what I am constantly telling you, we have to see all the circuit for this. Like, we have to see all the inputs for making a circuit. Okay, so if the code is 000 and if our D0 is on, only then we will get the output. Okay, so this will be our first circuit. The combination should be 000 and this D0 should be on. Then only we will get the first output. So this will become our first case. Then this will become our second case. The code should be, select line should be 001, and this D1 should be on. Only then we will get the output. So this will become our second sum of products. If we do sum of products, then this will become our second product. This will become our third product, and all these things, and this will become our last product. Okay. So if we make the products from this first case, it will be A bar into B bar into C bar into D0. D0 is not bar because D0 is 1. That's why we are using here as D0. So if we make this circuit, then it will the code will become as A is 0, B is 0, and C is 1. So the code will become A bar into B bar into C. And here we are having D bar. So that's why this will become a second circuit, A bar into B bar into C bar into D1. And same, how we will make this last circuit? How we will make this last circuit?
ABC.
Into D7 is also there, na? AB into C into D7. This D7 is also in the input. If we see the circuit, we have to consider all these inputs, okay? All these inputs. To make a circuit, we have to consider all these inputs. So that's why we are having this D7. So we will also add this. So here we will have one AND gate for this, 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 and so there will be total 8 AND gates for all the cases. Okay. And how we were doing sum of products, all these cases are there, all these 8 cases are there. We will add all these 8 cases. So one OR gate will be there. So if we make the circuit, here our 8, here we will use 8 this gates, 8 AND gates, and we will use this 8 OR gate. Okay. So for the first combination, it was A naught into B naught into C naught into D0. Okay. So this, if first case everything is correct, only then only we will get a output. Okay. So how we will make this A bar into B bar into C bar? We have used this NOT gate. We have used this NOT gate. So from here we are getting this A bar. From here we are getting this B bar. And from here we are getting this C bar. Okay. And from here we are getting this D0. If all are correct, only then we will get the output. For second case, it is 0, 0, 1 into D1. So 0, so A0 will come here. This B0, B dash will come here, and C is 1. So C directly, we are taking C directly, not from the NOT gate. Okay. So this is our second combination, second case. And we are taking this D1. So I will show you the circuit in this multisim. So this is the circuit. Okay. So for our case 0, 0, 0, so you can see this is on. Okay. So 0, 0, 0, this NOT gate is working. So 0, 0, 0, then this NOT gate is inverting to it to 1. So this is on, and this is also on. Okay. But you can see this, this D0, we have to switch it on. So we have included this D0. So if we switch it on, we can see this gets switched on, and here we can get a 1. If we click on any other circuit, this is not working. So if we do 0, 0, 1, so we can see this circuit here, we are taking a 0 from here, we are taking a 0 from here, and the 1 is the input from here, 0, 0, 1. Okay. And if we click on this D0, only then this circuit will work, and here we will get a 1, because this is OR gate. If any 1 is on, then it will work. Okay. Same way with 0, 1, 0, we will use this third circuit. So we are taking a 0 from here. So we have taken a 0, but NOT gate is inverting it and making it on. So this first part is on. So 1 is there. So we are directly taking this 1. Okay. And here 0 is there. So we are taking C, and we are using this NOT gate, and this is also on. So how to make it on? We have to switch on this part. Only then this part is getting switched on, and with OR gate, this is working. Same with 1, 1, 1. You can see here 1 is working. Here our 1 is working, and here also our 1 is working. Only one gate is not working. So we will switch on this D7. One switch is only not working. And if we switch on this D7, this circuit will start working, and it will give a 1. And from here, we will get a 1. If we switch on any other circuit, see only 3 is on and 1 is off. That's why it is an AND gate. And if we product this 1 into 1 into 1 into 0, so we have a 0. That's why these will not work. Any doubt how it is working?
Ma'am, here D also works as an input, right?
Yes, all these are also inputs and all these are inputs. So we have to consider these three cases and we have to consider whichever case we have to switch it on. Okay. So that's
What
why
values do D carry, ma'am?
hmm,
What values do D carry?
D 0 and 1. So like we have to code is assigned. I told you how code is assigned. So actually this D0 has been assigned the code of 000, okay, and D1 has been assigned the code of 001, and D2 has been assigned like that. The code is assigned. So first we will see the code. What is the code, and if the code is matching with the with whichever input, and that is on, only then it will work.
So D carries all the three other inputs.
No, this is independent inputs.
Okay, ma'am.
These are independent inputs. These are also independent inputs. So this is how we are making multiplexer using this logic gates. Okay, we have IC. So this is how we will construct this multiplexer using logic gates. So what is the advantages of multiplexer? It has less wiring is there, so complexity is less and the cost is also less. Otherwise, we have to uh, connect all the phones to other phones, and a more number of circuits will be there, and the cost will become more. So what is the applications? We use it as register selector in the ALU. Okay, we can also use it as switch, and in Boolean functions we can use it as half adder, full adder, encoder and decoder. So these are the applications. So if we have only one mux and we need we need a function of full adder and an encoder, we can use only multiplexer to make all these functions, to do all these functions. Okay, that's why we are using this multiplexer. We are making this multiplexer. Uh, Try doing this in Logisim, you will understand the circuit, okay, how it is working. Here is our code and here the switch should be on, only then it will work, okay. Uh, on Friday, we are having two classes, but your IAT, it is on Saturday. So I am thinking of, instead of that two classes, I will give it for your studying, and I want to take an extra class today. So you are comfortable with which? Everyone write your roll number here. So you want to do those two classes on next Friday, or you want to do an extra class today?
Class today only, ma'am.
So from 2 to 4, 1 to 2, is it okay?
Yes, ma'am.
Mom, we have lab today.
Okay. Then we will do an extra class on Wednesday.
Yeah, mom.
Okay. Okay, then you can leave. Just I have uploaded this IIT questions. Okay. I have uploaded this IIT questions.
Ma'am, do we need to submit it?
Yes, by Monday you try to do it in a copy and submit it. Because these will only come in exam. I will just give you the syllabus for your exam. So just go through these questions, and this last question is this in this logisim. Just do all this by Monday. Write in a copy, or you can also do in the Word file, however you like.
Ma'am, we have to answer all these questions and upload it in GCR, ma'am.
Yes. So these questions, like we have not studied this, so leave these questions. So
But many of the topics have not been covered yet.
yes. So whatever is covered, you just do it in one page, one question, one page. Okay. So that will be easier for you to compile and send it.
Okay, ma'am. Thanks.
You can leave.
Thank you, ma'am.
This will come in your exams. Okay. Just go through the questions in the weekend and cover all the topics.
Excuse me, ma'am.
Hmm.
Can you show that truth table of D0, D1, D2 like that? Yes.
So this is the truth table.
This is not this.
Hmm?
No, ma'am.
For which one?
ಫಸ್ಟಿಗೆ ಹಾಕಿದ್ರಲ್ಲ ಅದೇನೆ. ಫಸ್ಟಿಗೆ ತೋರಿಸಿದ್ರಲ್ಲ ಅದೇನೆ ಮ್ಯಾಮ್.
Can you say it in English? Truth table for what? This multiplexer?
D0, D1, D2 you explain that.
This part?
No, ma'am.
You need the circuit or?
In Google Classroom, ma'am. Will you share this in Google Classroom, ma'am, this PPT?
Yes, it is already shared. In PPTs, go to this class lectures. So this is actually the truth table. Here all the inputs are there.
Okay, ma'am. This is.
Okay, you can leave. Go to the next class.
Ma'am, excuse me, ma'am.
Yes.
Ma'am, you have given notes, handwritten notes as well as textbook, no, ma'am. Which one would be
Yes.
better to refer, ma'am, for examination?
I would say this handwritten notes is not written by me, so I have included everything in this PPT. Okay, so just go through the PPT. It will be enough.
This one, ma'am, PPTs which you are providing now.
PPTs. Yes, and I am also providing this video lectures. So just go through the video lectures.
Okay, ma'am. Thank
Ma'am,
you,
in
ma'am.
PPT,